Good afternoon, everyone. Am I audible? Am I audible? Can anyone reply? And is my screen visible? And is the screen visible? Okay, I think we'll wait for 1-2 minutes. Maybe some other will also join, and then we shall start after 1-2 minutes. Good afternoon, everyone. Am I audible to everyone? Am I audible?
Yes, sir.
Okay. So, good afternoon, everyone. I am Adnan Farooq Khan, and today is the fourth week of our problem solving session for the course Design of Power Electronic Converters, which is being taught by Professor Shabri Nath from IIT Guwahati. Every one of you know that this problem session we have on Sundays from 3 to 5 on every Sunday. And as we do, as we have done before this problem session, what I'll do is I'll go through the contents that has been taught in this week, give a brief overview that what has been taught in this week. Then we can move forward to the problem solving session, which shall help you in solving your assignments, which are more or less the same. The assignment that has been given is same uh, as the problem solving, as the problems that will be solved. So coming to the today's session, so I'll be first going through whatever has been taught in this week. Like previously, one thing that was remaining was the DSAT protection, that I hadn't touched it. And then after that, what had been taught in this week was about the bootstrapping. And after that, the other two topics was other gate driver related aspects, and with that the gate driver module was completed. And after that, what had been introduced is the snubbers, and why we need the snubbers, what are its advantages, and so on and so forth. And then different types of snubbers were discussed, like RC and RCD snubbers during the course. So yeah, coming first to the DSAT. So let us first go through what is DSAT protection. So, and what does this imply? As the name in itself, you can see DSAT, it is like from moving away from the saturation region. And uh, what is this protection? DSAT protection, this is mainly an overcurrent protection. You know that if you have a device that is here, IGBT, we have the three terminals, collector, gate and emitter. Whenever we give some we give some VGE voltage, then uh, as our VGE voltage goes beyond the threshold, our device starts to conduct. And then what will happen with the increase in VCE, our current will increase. And if you can see, for a certain if we then if the VGE voltage is increased, and we can go from active region to the saturation region. And what we want here is we want to operate this devices in the saturation region that we had discussed. Usually where we operate the our devices are in like two regions, either in the off state, that is the forward blocking mode, or in the on state, like during the in the saturation region. And why so? If you can see, in the active region, we there is a lot of voltage drop. If you can see, VC very high, there is very high amount of the current, and which can cause very high voltage drop in the devices. Also, like in the active region, there is only a limited amount of the current, some current that can flow. and mostly we want to have our operation in the saturation region. So as the name implies, it is desat, that is moving away from the saturation region. So what happens is, why do we need this sort of a protection? First is like this case, why do we need this protection? So there are a number of one thing is, mainly when we choose our devices, we had seen our devices are rated for certain voltage and current levels, and and after and if we have the devices that our current will go beyond that rated level, then it can cause a damage to our devices. Also, if there is a huge amount of current that will flow through the device, there will be a losses across the device. I square R losses that RDS on we had seen, and our devices may heat up, and which may in turn damage the device. So what we need to do is, we need to protect our devices from these high currents. So one way is like, we may sense our currents. As soon as we see that our current has gone beyond the limit, then what we can do is, we can give we can sense that current, and as soon as it will go beyond the rated current value, then we can tell our controller to turn off the pulses, and which will then turn off our devices. But what happens in that case is, like, there is some time delay associated with that thing, because there will be some time that will go into the sensing, and after that, when that thing is interpreted by the controller, and controller will give its commands, and overall there will be some time delay associated with this thing. So what can happen within that, if our current is too high, that can cause the damage to our devices within that time frame in itself. So that we think we don't want, but we want something that is very faster than that thing, which can cause, which can protect our devices. And one such protection is this DSAT protection. And what is this and what is this DSAT protection? As I earlier told, let us say we have an operating point here. If you can see this green dot, there is some current that is flowing through this device, and if you can see, if my current goes from this green dot to this red dot, that means our current has increased for a certain VGE. You can see that our operating point has shifted from the saturation region to the active region, and in this active region there will be a very high voltage drop that can damage our device. So shifting from this saturation to the active region, shifting from this saturation region, that means DSAT, from where its name comes, DSAT protection. Now what do we need to do for the implementation of this protection? What we can see is, here, whenever the current flows through this VCE, if this current increases, this may cause an increase in this drop VCE voltage. If we are somehow able to detect this VCE voltage, we can say that there is an increase in our current. And if we are able to set a threshold limit, let us say our current increase by a huge amount, and then our drop will increase, and if we compare that drop to some preset value, and if our drop increases beyond that threshold, then it can set a signal to the grid driver to withdraw the pulses, and our device will be turned off. This is like how the DSAT protection will operate. So we'll go into the device. There were many ways to implement this DSAT protection. So, one such way was taught during the course, and here I shall discuss another another way to implement the DSAT protection. Here, if you can see, there is a gate driver IC UCC21750 by TL. This is the DSAT mechanism that is inside the gate driver IC in itself. The gate driver IC has these pins. DSAT pin here, if you can see the cursor. So what is being done is that this DSAT pin is being connected to the collector or drain terminal of the MOSFET or IGBT, and this is being connected through an R and some diode, and this diode should be rated to very high voltage. Why so? Because when the device is in off stage, there will be a huge amount of the full DC bus voltage that will be across this device, and that voltage and this diode should sustain that amount of the voltage, because that voltage will come across this diode. And if diode is not rated for high voltage, this diode may get damaged. So if you can see here, what happens during the off stage, there is no pulse to this, and all the DC bus voltage comes across this device, and which will reverse bias this diode. Now coming to the DSAT protection, if you can see beyond to the left of this blue line, this is all the things are inside the gate driver IC. So what we have is, we have a current source that is inside, like this. If you can see this arrow, this is a current source that is inside the gate driver IC that supplies some current, always supplies this current when the device is turned on. And we have a comparator circuit here, and we have some voltage, like some preset value, we call that VDSAT. Like here it is given it the 9 volts, and this voltage, and whenever this voltage at this DSAT pin is greater than this 9 volt or the preset DSAT threshold DSAT voltage, then our DSAT protection will get triggered. So how is this done? Is whenever our device is turned off, that I told you, like this device will block whole voltage, and our diode is in reverse direction. So what will happen is, as soon as our device is turned on, this device starts to conduct, and the voltage at this C point, like VCE, is measured. Like this VCE voltage drop is measured, and the voltage at this point, if it exceeded and is compared with this VDSAT threshold DSAT voltage, and if this VCE voltage is greater than this VDSAT, then our DSAT protection is triggered. So what will happen, like usually we have our rated current that will flow through this collector emitter, and we choose this R and D in such a way that at our rated or the maximum current, that the potential at this point doesn't exceed this threshold voltage. So our devices, so our DSAT protection won't get triggered. So what is happened is here, as soon as our device is turned on, this current will flow through this R and the diode through this drain, and this will cause some voltage drop across this R, and there will be some voltage drop associated with this diode as well. And the sum of this drop across the resistance diode and the drop across the VCE drop will come across this DSAT pin. Usually this voltage is less than this threshold voltage at our rated conditions or at our peak conditions. But what will happen if suddenly our current through this collector increases? So when this current increases by a large amount, the voltage drop across this VC will increase. As soon as this voltage drop across this VC increases beyond the threshold, our DSAT protection will get triggered, and this will DSAT protection is itself in our gate driver ICs, and which will cause our pulses to shut off or go low, and which will in turn turn off our devices, protecting our device. That is how the DSAT operates. And if you can see here, there is another capacitor here, capacitor that is called blanking capacitor, that is connected across a device. So why this blanking capacitor is used is, if you can see, before turning on our device, the voltage across this device is very high, like full DC bus voltage, and that will reverse bias our diode. But what will happen, as we turn on this device, this voltage will decrease, and there will be a point that this voltage will be greater than this 9 volt, and that can falsely trigger our DSAT protection during the turn on condition. When we turn on this device, because initially, like, the device is turned off, it is blocking the full voltage, this diode is reverse biased. At some point this diode will get forward biased, but if during the turning on, if this voltage at this point is greater than this threshold 9 volts, that our DSAT protection will get triggered on. So we do not want that thing to happen, but what is usually done is we have this blanking capacitor here. So whenever we turn on this device, this current will start to flow, and this current will cause this capacitor to charge, and voltage will start to build up uh, in this capacitor, and it will take some time for our voltage to build up across this capacitance that will come across this DSAT pin. And usually this C blanking capacitor is chosen in such a way that the build up in the voltage, that the build up in this voltage is greater than the turn on time of this device, because the voltage across this should build up in the time greater than the turn on time of this device. Only then this false triggering of the DSAT protection is taken care of. For that purpose, this C blanking capacitor is used to limit the false DSAT protection in case of a turn on, in case of turn on of the device. And usually, if you see, when you have a gate driver, we have this DSAT and these pins given. Only the external circuitry that we have to add is this blanking capacitor, resistors and diode that we can choose as per our need, like what are the ratings and what is the turn on time of this device. Accordingly we can choose these blanking capacitor, resistors and diodes. This was about like the DSAT protection, a way to have the overcurrent protection in our device, and this means of protection is very fast. After the DSAT protection, the other topic that has been discussed is the bootstrapping. The first thing is we want to know is why we want to have this bootstrap circuit. Previously, during the previous week, we had seen if we have a half bridge circuit, like we have an S1 and S2, and if we want to switch them, and we have to provide the VGE voltage, this is the gate terminal and this is the S. We provide this VGS voltage for the top and bottom devices in order to turn them on, and we had seen that the VGS voltage in case of the bottom device was provided with respect to this ground. But in case of this high side device, we had seen that that voltage was to be provided with respect to this floating point supply, because when this S1 is turned on, we have a voltage VDS across at this point A, and whenever this S1 is off, we have a voltage 0 that is across at this point A. So the voltage at this point A is fluctuating between 0 and VDC. So in order to turn on this device, we had to provide the VGS voltage with respect to this floating point, and we had to take care of this floating supply in order to like turn on our devices. And one way to turn on our devices, taking into the consideration this floating point supply we had seen, is the one way to do is the isolated DC, was by having this isolated DC to DC supply, which was able to like provide take into the consideration this floating point supply and provide the VGS up with respect to this floating point supply. But at that time itself, I told you like that is an expensive way of doing this thing, like taking into the account this floating point supply. And I had also told you that one way, a cheaper way, an economical way to do is by having the bootstrap circuitry. So we shall see how this bootstrap is implemented. Just a minute. How this bootstrap is implemented, and so on and so forth. So what this bootstrapping it provides an alternative for high side gate driving, as we had seen, high side gate driving, and this way is an inexpensive way. Rather, if we had used the isolated DC-DC converters, that is an expensive way of doing this thing. So how this bootstrap works, and now we'll see. So this is the bootstrap circuitry. As you can see here, we have an H-bridge leg here, S1 and S2, and to drive these things we have a high side circuitry and a low side circuitry. And we know that at the point A we have a floating supply, like this point is a floating point and it has the voltage of like 0 and VDC. Whenever the S2 is on, we have a 0 volt, and whenever the S1 is on, we have a VDC voltage at this point. Now we'll see how this bootstrap circuitry will help us in driving the high side switch. So for this bootstrap circuitry, if you can see here, what needs to be kept in mind, first we have to turn on this S2 switch. That means this bottom switch we have to turn on, and after that the S1 switch. So how this is done is like, if we turn on this S2 switch, using this low side circuitry, there is some VG voltage that comes across, like let us say plus 15 volts needed to drive this low side switch. Now that means that this S2 switch is now on. So if S2 switch is on, you can see this ground point will come here, and what will cause is, it will cause this bootstrap diode of the bootstrap diode to forward bias. When this bootstrap diode is forward biased, and what it will cause is like a current will flow and it will cause this C bootstrap to get charged, and the path of this will be in a way, if you can see my cursor here. So what will happen? So when the bottom switch is turned on, our D bootstrap is getting forward biased and it will cause our C bootstrap to charge. And if the bottom device is turned on for a certain time, that in that time this See, bootstrap is charged to the full potential of this VG, like let us say 15 volts. Is C bootstrap is charged to the full voltage of uh, plus 15 volts. So when this S2 is now turned on off, what will happen is like this whole voltage VDC will come across here at this point A, which will cause this diode to reverse bias. So now what will happen is, as soon as this S2 is turned on off, there is a voltage across like a 15 volt across this capacitor, and this voltage, if you can see, this point is connected to our source, and now this voltage will drive our high side switch. If you can see, that is with respect to this source point. So in this way our high side switch is turned on using this bootstrap circuitry. Also you can see, we had seen like in order to turn on our device we need some charge, like gate source charge, in order to turn off our devices. In the case of a bootstrap circuitry, like for the bottom device it is provided by the VGA source, but for this top device this gate charge is provided by this C bootstrap. And we now in a nutshell we can say, whenever this bottom device is turned on, this C bootstrap diode bootstrap is forward biased, and discharges are this C bootstrap. Bootstrap is charged to the threshold voltage, and after this S2 is turned off, like this D bootstrap gets reverse biased, and this C bootstrap will provide the charge to turn on this top high side device. This was about the bootstrap. Like there is this was the circuitry, how it has been implemented. There are a number of ways how to implement this bootstrap, like that has been discussed into the course, and you can go through the transcripts in a detailed way how this bootstrap works and the working of this bootstrap. But the thing is, like it works in a way like I had told you, the main principle is this, that bottom device is turned on, our bootstrap capacitor gets charged, and when our bottom device is turned when our bottom device is turned off, this capacitor provides sufficient gate charge for the top side device to turn on. So now, but we can see this bootstrapping had some certain limitations as well. So if you can see here, this bootstrap we had seen, like with the isolated DC-DC converters, there was an isolation between the signal side and the power side that was being provided by this DC-DC converters. But here you can see there is no isolation from the signal side and this power side, and if there is any noise on this power side, that can get reflected to the signal side as well. That may cause the false triggering in some cases. The other thing is, like you have to keep in mind that this bootstrapping can be only implemented for the half bridges. So here if you can see, this is a half bridge, like a half bridge uh, circuit, where we have a top device and a bottom device, and it need not to be that the bottom devices should both of the devices should be switches. We can have our bottom devices as diodes as well, and that thing has also been discussed in the course, and you can go through that how it is implemented in that, how it works at that time. We can go through the transcript as well as the lectures. But the thing here is, in a nutshell, you have to keep in the mind that this bootstrapping thing is only applicable for these half bridge circuits, where if you can see most of our like topologies, be it buck converter, boost converter, buck boost, we have this half bridge leg uh, in each of these converters, be it like rectifiers, inverters, and so on and so forth. So we can have this bootstrap in all of these circuitries. The other thing is like what we have to keep in mind is, like I told you, the charge for this to turn on this device is being provided by this bootstrap capacitor. So the other limitation of this bootstrap is like it is only used for the low gate current, for the circuitry which require only low gate currents. Wherever we have a very high gate current requirements, like this bootstrapping is not a feasible option. Why so? Because like if in order to provide that high gate current, what is needed is we need to have this very high value of this capacitor in order to provide for such high currents. But we can have the high value of this capacitor, but the disadvantage of that thing is during the turn on of this bottom device, this capacitor may take a large time to get fully charged to the full potential. And if that time, that may limit our switching frequencies, because we know that this capacitor gets charged whenever this bottom device is turned on, and if we have very high switch and if we are operating at very high switching frequencies, then this capacitor may not get fully charged, and our top devices may not get like turned on, because the potential across this capacitor hasn't been developed or beyond that threshold that is needed to turn on these top devices. So mostly this bootstrapping is used for like the devices which have the low gate current requirements. And also it has to be kept in mind that the switching frequency of the devices, it has some limitation on that as well, because like in order to charge this bootstrap capacitor, we need to have this time interval so that this capacitor gets charged. We have to keep that thing in our consideration. We cannot have the switching frequency very high so that our like bootstrap capacitor doesn't get charged to the full potential, then it cannot drive this high side switch. So that is the other limitation of this bootstrap. This was the other thing that has been discussed. Now there were some other aspects that has been discussed about the gate drivers. So one such is like this pulse pulse transformer based gate drivers. Up to this point, like we had seen optocoupler based uh, gate drivers, where we had on the primary side like a light emitting diode. When we applied this PWM across it, then it caused the diode at the output side to turn on, uh, and so on and so forth. The other way to do it is using the transformer here. You can see here we have a PWM voltage at the input of this the transformer, that varies from 0 to VDC and so on and so forth. And we have a transformer. If you can see at the output, we can get that voltage here as well. So the other aspect in the gate driving that we had seen is why we require this gate driver, is we needed the level shifting in terms of the voltage and the current, so that our controller side was not able to provide that amount of current in order to drive the devices. We needed to do the level shifting in terms of the voltage and the current requirements and so on and so forth. But here, and for that we use the additional circuitry. In terms of the transformer, we can see if we have some voltage and at the input, we can certainly step up that voltage at the output, and so on and so forth. So we need not to have any additional circuitry here as well. But the downside, but this has some other limitations as well, like at very that has been discussed in detail. At like we know that this transformer cannot process the DC, but since our this PWM is varying from V0 to VDC, we require this capacitor as a DC blocking capacitor, which would block the DC and which would then shift our this primary PWM by some DC amount, and then that at the output we can get that similar voltage, but that won't be able to drive our voltages. Then we need some reshaping circuit, that you can see some diodes and RG and how that is done, and you can for that you can go through the lecture, and this has been discussed in the detail. This was the downside of this using the pulse transformer based gate driver. The other thing is like with some higher frequency we see uh, a change in the duty ratios, and how that is as happening, that has been discussed in the detail in the course. For that you can see the transcript as well as the lectures. So here, like, this was a brief gist, like this type of gate driving we can also implement. uh, yeah, implement additional to the optocoupler based gate drivers that we had seen earlier. So the other thing here is the earlier, like we had seen this the structure of our devices, where we had of the MOSFET, like we had the drain, gate and source. We had seen we had this parasitic capacitance between these terminals. Besides these parasitic capacitance, like we have some other parasitics as well, like this LS. If you can see, there are some traces between the source and gate, which will have some inductance, that will have some parasitic inductance as well. And then we have some RG gate resistance between this G, and then we have some VG voltage. But then after that, this voltage, there will be, this circuit will be an RLC circuit, and whenever we apply the voltage, there will be some ringing and spikes, which may, if that ringing and spike may go beyond the limit, that may cause a damage to our devices. So we have to keep in mind the effect of these parasitics, and we will see the ways how to tackle these things, and this has been like discussed in the lecture as well. This was another aspect to keep into the consideration, the effect of these parasitic components during like the gate driving and turning on and turning off these devices. The other thing is like the speed enhancement. So we had seen, like, in order to turn on our devices, like we had some RG on. If we want to like delay our turn on by some amount, we will increase this RG on. But when we like turn off these devices, had there been not any additional circuitry that you are seeing, like this RG off and diode, then our device would turn off through this RG on. And as we had seen during this paras, what we have is here is the capacitance between this G and S, and there may be some parasitic inductance as well, which is very small, and we can neglect that. And what mainly this circuit then formed is an RC sort of a circuit, and it may take some time, that will depending upon this RG and C, of some time constant, in order to charge and discharge these capacitors. So what we need is during the turn on, as we had seen during the turn on of this device, when we have one leg and one device is turned off, we have a reverse recovery in one of the devices, and that gets translated to the other device of that leg. So During the turn on, we have to keep in the mind the effect of that reverse recovery. That is why, like, the turn on time, we usually keep the turn on time higher than that of this turn off time, in order to take into the account that reverse recovery effect, or reverse recovery of the diode effect. That is why this RG on is kept on the higher side. But during the turn off, we want to turn off as fast as possible, so we do not want to like turn off through this RG on. For that, like, we have included some additional circuitry. If you can see this RG off, the value of which is very like small, and if you can see, when this voltage goes to zero or a negative, that will cause this diode to forward bias, and this capacitor VGS will be at a plus 15 potential, and it will like uh, discharge through this path, through this path and the voltage across this capacitor will decrease. So in this way, like, we can turn off at a faster rate compared to the turn on. And usually, like here, if you can see, we these are at the same point, but in the current or like modern gate drivers, we have the separate pins for this turn on and turn off. The only that are provided, only what we have to do is we have to like add additional resistors circuitry to that thing, and we have the separate like pins for this on and off, and all that thing, this thing is internally in the gate driver in itself. So this was about the gate driver thing, and after that gate driver, the other topic that had been introduced is the snubbers. So the first thing is, we need to see why do we need the snubbers, what is the need of the snubber circuits. So like, if you can see, and as earlier see this uh, picture here, we have a circuit of an H bridge, and across that we have is connected DC voltage source. We know, like, till then, till like now, we had seen the ideal cases, but in the non-ideal cases, we have some parasitics there because of the leads power traces. Like, if we have some leads, it will have some resistance and some inductance, and if we have some PCB, if we have PCB traces, there will be some parasitics, the parasitic resistance and parasitic inductance. And if you can see, and that this parasitics are between any 2 points, like any two points that are being connected through a lead or a trace, and so on and so forth. And if you can see here, between this DC and drain, there will be some parasitic resistance and inductance as well, and so on and so forth. From this negative terminal to the source of the bottom device, there will be some inductance and resistance between these terminals as well. But here, what is being done is, these parasitics has been lumped. What we assume is, all these parasitics has been lumped here at one point. And what this will cause, this RLC, if you can now see, now we have like L, R, and we know we have some in the device itself, we have a capacitance between this drain source, and now what it forms is, if you can see, is an RLC circuit. And if we know, since these are the parasitic values, the value of the value of these elements will be very small. Since the value of this R is very small, so this RLC circuit will be an underdamped circuit. And when we like turn off this device, and the voltage needed need to rise. If you can see here, when we turn off this device, then voltage needs to build up to this steady state value of some value. But because of this RLC circuit, there will be some ringing and overshoot as well, and it can go beyond that thing because our system is under damped. We need not, and if this if this peak value will go beyond the rating of the device, it may cause damage to our device. So why we need snubber is like we have to think of a way where we can limit these ringings, this dv by dt of the device, which can cause any harm to our devices. So if you can see here that I had earlier told you, because of this parasitic RLNC and RLC circuit is formed, and due to the small value of this RP, this circuit will be under damped circuit, and because of that we may have some ringing and spikes. And whenever we turn off this device, when this voltage build up, in order to gradually build up from the 0 to the VDS value, there is some overshoot in this voltage, and we don't want our overshoot to go beyond the rating of the devices, so that it may damage the devices. So now we'll see how these numbers will work and how it will limit this peak of this device. So if you can see now here, now this what these numbers do usually, like what had been discussed during this week, is like two type of snubbers, RC and RCD snubbers. Here we will take like I'll give briefly just about the RC snubbers. In a similar fashion, there is like this RC D snubber as well, that has a diode etc compared to the RC. And you can see that both of these in detail in the transcript, as well as if you can go through the lectures. So if you can see here, what is being done is, what we have across this device is, we have a additional RC circuit we connect across our device. What this causes is, it cause our RLC circuit parameters to change. We know, like these parasitics are not in our hand, and how well we may design our circuit, but we cannot avoid these parasitics. There will be some value of this some value of these parasitics that will always be there. There will be always some value of the parasitics that will be there. But what is in our hand is, like we have the value of we can like change the value of this R and C. By changing the values of this R and C, we can change the overall parameters of this R and C, and by changing these we can limit these spikes and ringing during the turn off of our devices. So during the turn off, what we see is, we can see the turn off, to what voltage this spike can go, then we can limit it. You will go through the calculations about what are the values of this R and C, how to calculate the values of R and C. That has been discussed in detail during this week, during the lectures this week. So I'll give briefly about that thing. So what are the advantages of this RC these numbers is, like they will reduce, as I had discussed, is like it will reduce the voltage spikes. Also, it will limit the dv by dt, as discussed, it shall limit the dv by dt and di by dt across the devices. Also, you can see, if you can see, like now there is a path across this device through this R and C. So during this turn off, some current may flow through this, and this can like distribute our switching losses. This may reduce some of the switching losses across these devices, and those losses will come across, will get dissipated across this RS, and that may help, like there won't be much switching loss across the devices, and our devices may not get heated up to the very high temperatures, and which may sometimes damage our devices. Also, like by using these snubber circuits, there may be a reduction in overall losses in the devices. Also, as we discussed, like these snubber circuits limit the dv by dt and di by dt uh, uh, across the devices, and which may in turn like reduce the EMI issues, which are mainly due to this dv by dt, or by the rate of change of the voltage and the currents. So now we shall see about this number analysis. We shall take up only one here, like because of the limitation in the time, we shall take the RC snubber here, uh, and in the similar fashion you can, and there is the analysis of the RCD snubber as well, that has been discussed during the course. You can go through the lectures and the transcripts as well. So here, if you can see here, the device under here, the device here is this diode, and across this device is connected an RC snubber, and with that thing, then we have in series this some parasitic inductance as well. And we know that our device has to block our whole voltage across. If our this total voltage to be blocked by the device is this E, and here this small e is the voltage that is across this device. How it is done is like we see, when this initially this device was conducting, and there was some current that was flowing through this device. Now as soon as this device is turned off, so current will decrease. It is the current here is shown in this fashion because we have taken this ID reference in the opposite direction. So the current will decrease, and there will be some reverse recovery current in the diode that we know. And as soon as this current will reach the reverse recovery current, and this diode will start to block, what will happen is this current will have a path through this RC snubber. This current will shift from this diode to this through this RC snubber, and when this current will flow through this RC snubber, the voltage will this capacitor will get start to charge, and this voltage will start to appear across this device. If you can see earlier, as soon as this current is shifted, and this current shifts from this device to this through to this RC snubber at reverse recovery current. So you can see this current, when flows through this R, this will cause some voltage drop across this voltage drop, that will be equal to RS into IRR, and that current will flow through this capacitor, and which cause the capacitor to charge, and this voltage will then reach to the peak, will be charged to this peak of this E voltage, but there will be some oscillations, and that we can limit or dampen by appropriately choosing this R and C values. And we shall see how to like design these R and C values. In this way, like our snubbers will limit this ringing across this device. So how it is being done is the analysis. What we do is we write the KVL equation for this loop, for this outer bigger loop. If you can see, we will write, we have on this R, C and L. We write like the KVL equation for this, and this will be equal to this overall voltage that is to be blocked by this device. And the other KVL equation we shall write for this is like this diode, and in this loop where we have a diode and this parasitic inductance, that will be equal to E will be equal to E minus LP del di by dt, that is the voltage across that will come across this device. What is to be kept in mind, we have we take into the consideration some initial conditions. So, the initial conditions that we take into the account is like, we assume that initially that this capacitor is fully discharged. Also, what the other initial condition, sorry for the other initial conditions that is taken is like this the current through this snubber will flow at the reverse recovery current IRR. And what is also the other assumption that is being taken is that initial voltage drop across this device E will be equal to, because what we assume is that this capacitor is initially discharged, and the only drop across this branch will be IRR into RS that will come across this device. That will be E at the initial condition will be equal to RS into IRR at the time, and this the current through will flow through this snubber path. That we write these equations. After that, what is being done is then we solve these equations. And that has been discussed in detail in the course. I shall not go through those things here. So, but I'll go through the steps that you will follow in order to like solve these equations. So what the first step that is being done is like, we solve the differential equation for the IT, that is the snubber current here at the time t. And we can do for that different cases, like we know for RLC circuit we have underdamped, overdamped or critically damped circuit. And using the initial conditions that I had already told you, we can solve this for this IT. And when we solve this, when we get this snubber current IT, and what is being done is then we substitute this IT in this equation. E is equal to, because we know E LP may be given the parasitics, then we can get the voltage across this device as well. And after that, like we can get this we can find the time at which like E will be maximum. That E is the voltage that is coming across our device, like small, where we can do dE by dt. We can like by set dE by dt equal to 0. Then what we can do is we can find E1. What is E1? E1 is the peak of this voltage that will come across this device. And what we want to do is, we don't want this E1 to exceed our device specifications for which this device is rated. So when we are able to like find E1, then what we will find E1 by E, that is the normalized value, because E is the steady state value, and the ratio of E1 to E will give us the peak to which are like the voltage will go across this device. Let us say this E1 by E is equal to 2. That means if our rated is voltage that will come across this device is 100 volts, that the peak voltage that will go come across this device will then go to 200 volts, and so on and so forth. And after that, what is being done is we calculate dV by dt average, which is equal to like E1 divided by T1, that is here E1 in T1 time, is then being calculated. Usually, if we solve this, we have a very big equations to solve for this, which is very difficult to do the analytically, and more or less we rely on the graph that I'll show how to do, what are the graphs that are taken into the consideration to solve for this equation. So before going to that, there are some terms that are used, and these equations are solved in terms of these terms only here, and these terms are then listed in the graphs, and we can get the values of these for a particular specification. So one thing is the natural frequency, undamped natural frequency, that is given by 1 divided by LP into CS. There is another factor that is called decremental factor, that is RS by twice LP. Then we have some damping frequency, which is given by omega d, that is the natural frequency minus this alpha square, which is the uh, decrement factor. Then there is another factor, that is the damping factor, that is given by xi, that is equal to RS divided by twice root LP by CS, and so on and so forth. The other another term that is being used is initial current factor, that is given by chi, and that is given by this expression. And how we demand how we find this chi is chi will be equal to the energy that will be stored in the inductor, parasitic inductor, to the final energy that will be stored in the capacitor, in our snubber capacitor. And also, depending upon this xi factor, we can have different cases like underdamped, overdamped, or critically damped conditions. And all of the equations that we get for these snubbers that we had earlier discussed, these differential equations that are solved in terms of these factors. So as I told you, the solutions for these equations is these are very tedious equations to solve by hand. You can use some MATLAB or some software to solve these devices, and these are the equations for the different xi conditions. Like when we have xi less than 1, that is under damped condition, then we have to use this equation. For overdamped, xi greater than 1, then this equation comes for this E1 by E that we had seen. And for critically damped, this is the equations. And usually these equations are very tedious to solve, and you may use some software in order to solve this equations for RC snubbers. These equations are for the RC snubbers, and you can go through the analysis of the RCD that has been taught during the week, and go through the equations for those as well. But there is another way to solve this. Is the other thing is, before designing the snubber, what is being kept in is there are the three factors we had seen for which we will design these snubbers. The first thing is, if we want to design the snubber for the minimum voltage peak, that means we have a limitation on some voltage peak that it should go, and it should not go beyond, the voltage peak should not go beyond a certain voltage. Then we design our RC snubbers with regards to that, so that our voltage peak is limited. The other, for other this design, this RC snubber is being limited to is minimum dV by dt. So we can design our snubbers in order to limit that. We shall go through our problems how that is being done. If we want to limit this dV by dt, we can design our then design our snubbers according to that as well. The other design is that we have a compromise design, we need not to have a minimum voltage spike criteria or a minimum dV by dt uh, minimum dV by dt criteria, but a bit of both. We have a minimized product of both voltage spike and dV by dt. And like these are the three ways for which we can we usually design this RC snapper. And in the problems part we shall go how this is being done. So the other way to do this thing is like we can use that we had discussed. There are certain factors like xi, that is the damping factor. We have an initial current factor, that is chi, that is given by this axis, and we have the normalized peak voltage, that is E1 by E. And if you can look at this graph for a certain chi value, if you can see let us say zero point 0.4, you can see that normalized peak voltage with some damping factor first decreases then increases, and that is for different as well. If you can see, there is a minimum point for different initial current factors for this normalized peak voltage as we like change this damping factor from 0 to like 2.5 and so on and so forth. In a similar fashion, for a certain, then we have some different minimum points. In a similar fashion, for a certain like xi, and if we increase the chi value, then we have a different normalized E1 by E voltage here. So what is being done, and these minimum points voltage are like plotted here in this graph. Well, we have that this on the x-axis we have the initial current factor chi, and on the y-axis we don't have any like what on the y-axis we have different graphs for xi and normalized frequency, and both of them the values are on the y-axis, because this normalized peak voltage E1 by E both have the same units, and this will be a dimensionless quantity. Similarly fashion, we have the xi, and both of them, the values of both are taken from this y-axis. Let us say we want to have E1 by E ratio to like around 2. That means we want our peak can go up to the twice of the rated device voltage. So at that time, what is being done, if we have if we draw a vertical line, we can have some initial current factor for that, that means chi, we can get some chi factor for that, and at the same time it will cut the xi graph at some point, and from that xi we will draw a horizontal line that will be the value of the xi at that point. So for having a E1 by E around 2, there will be a some value of xi and chi at that point. In a similar fashion, we can, as per our need, that you will see how this is done in the problem solving session, we can calculate different xi and chi values for a particular thing. And when we get these values, we can like put these values here in these equations that we will see in the problem solving session, uh, and calculate the values of Cs and Rs, that is, these are snubber capacitor and resistor values. This was about the snubbers that has been discussed in this week, and like in detail, like the analysis of the RC and RCD snubbers that has been discussed during this week is given in this paper. If you go through this paper, the whole analysis is by this paper has already been discussed in the course, and this has already been told by ma'am that you can go through this paper for the detailed analysis. So this was about the snubbers. Now what we shall go is we shall go through the problem solving session. So this is our first problem, and like we shall take a break for like uh, 2-3 minutes, and we shall like join from 4:20 and start the problem solving session. So, hello, am I audible? Audible? Can anybody reply?
Yes, sir.
So coming to the problem solving session, like the problem that we are going to discuss here is a buck converter is designed using two MOSFETs. Like instead of a diode, we have a another MOSFET here, like sort of a synchronous buck converter, and the part number of the MOSFET is given, like that is this IRF 540 in PBF, and if you can search this, you can get the data sheet of this device. And what is being done is one MOSFET is used like a switch by giving the gate pulses. So second MOSFET is used like a diode, that is its body diode is only used and no gate pulse is given. So uh, despite having two devices like MOSFETs, only the gate pulses are giving to the one device. And what is given is the input voltage of the buck converter is 50 volt. We are given is input voltage is 50 volts, and also it is given is the value of the parasitic inductance is estimated as 8 nanohenry. This has been done by some tests and by some analytical method, where we use some softwares like Maxwell lenses and so on and so forth, and they have calculated this value. So if you can see, this is the buck circuit. So where we have a V in is the voltage, and we have the two devices. Let this be my first device and this be second device, and we have inductance, capacitance, and then there is an output. So it is been told like the one device to one device the switching pulses is giving, and another device is in the off stage. So when it is told the switching is given to the one switch, that we assume it is to the high side switch and the main side switch, and this device is in on this device. In another device is always in the off mode, and only the diode of this device conducts. Now what we have to do is we have to design the RSC snub across this device, and we shall see what are the subsequent questions that are being asked. So here you have to remember, like LP is given 8 nanohenry and input voltage is 50 volts. So the first question is, from the data sheet, the dV by dt limit for the body diode is obtained. So what we have to go to the data sheet of this diode, now this MOSFET, and we have to see the dV by dt limit. So if you see the data sheet, where we have different parameters that are given, like ID at 25 degree, drain current at 100 degree, that had already been discussed what are these mean in the previous problem solving session. And then we have power dissipation, gate to source, and so on and so forth. And there is one parameter that is given is dV by dt, that is peak diode recovery. So it is giving, it has the maximum value of the 7 volt per nanosecond. So the answer to this first question is it is 7 volt per nanosecond. You have to only write the 7, because volt per nanosecond is already given. So the answer to the first question is 7 volt per nanosecond. You don't have to do anything, just download this data sheet. If in your problem solving session problem set that has been given to you, there is a question like this, you have to just download and see for this term, and there will be the value of this term, dV by dt limit. Now coming to the second question is, using the typical values of QRR and TRR given in the data sheet, the reverse recovery current is calculated as. So if you go through the same data sheet, and there are certain things that are given is continuous source current, that is given 33 amps, pulsar it can go up to 110, that has been discussed why the pulsar is high during previous problem solving sessions. And with respect to this forward voltage block, forward voltage drop across the diode is given. Then we have this TRR, reverse recovery time, is given, and what is being done, we have the like two values. One is the typical value, another is the maximum value. For some conditions that is being measured, we have the junction temperature of like 25 degree and current is like 16 amps at that time, and di by dt is 100 amp per microsecond at that time. So in the question in itself, it is taken like we have to use the typical value. So the typical value is 115, and QRR is reverse recovery charge. That is, in that itself we will use the typical value, that is 505 nanocoulombs. Now with these values TRR and QRR, we have to calculate the IRR. Now if you can remember the reverse recovery, how the graph is at that moment, then that is like in this way. In this way, if you can see, there is some voltage ID that is flowing initially, then when the device is turned off, then this will go to 0, and after that there will be some reverse recovery, and then the current will come back to 0. So here what we'll assume that this QRR is a perfect triangle, and we are given is TRR is given, that will form the base of this triangle, and what is given is what we have to calculate is IRR, that will be the peak of this triangle. We are given is QRR and TRR, and if we know the area of the triangle is given by 1 by 2 base into the altitude. Here QRR is the area, total area under this T, because I dt will be equal to Q. So the area under this I and T will give us Q, and QRR will be half, that is 0.5, base is TRR, and the amplitude is IRR. So here the parameters that we know are QRR and TRR. If these are known to us, then we can calculate IRR. Are you getting? So IRR will be equal to twice QRR by TRR. So we have QRR is like 505 nanocoulombs, and TRR is 115 10 raised power minus 9 nanoseconds. So if we like do the calculation of this, IRR will come out to be equal to 8.78 amps. You can see here like ID was flowing, the current that was flowing through the diode was 16 amps, and the peak is going up to like reverse recovery peak is going up to 8.78 amps in itself. So you can see the effect of this reverse recovery here. So the answer to this second question is 8.78 amps. So here now we have calculated the IRR as well. So after that, now what the question wants us is to design the RC snubbers. So this wants us to design the RC snubbers based on, like we had seen, the limit, the peak. The second thing we had seen is limit the dV by dt, and third thing was the optimal device, a compromise device where design where we had the product of this minimum peak and this dV by dt will be minimum. So we shall see all those designs here, but what is given here is, what we have to take into the consideration is peak voltage limit is E1, that is given to be the twice of the input voltage. That is the first thing that is given to us, and the other thing is dV by dt limit is half of the dV by dt limit in the data sheet. We had seen earlier the dV by dt limit that was given 7 volt per second or something like that. Here 7 volt per nanosecond, 7 volt per nanosecond that is given, and we have to take the half of that, that is 3.5 volt. Now we shall design the first. What it is telling is, first design the snubber by limiting the peak voltage. First we will see the design of the snubber by limiting the peak voltage, how it is being done. The third question first asks us is, what is the value of E1 by E is. So anybody, like in the previous slide itself it was given, can anybody answer this question if you are paying attention? What is the value of this E1 by E here? Anybody? Nobody? E1 by E, we want this ratio, not E1 equal to 100 volts. I am not asking what is the value of the E1. I am asking what is the ratio of E1 to E. So if you can see in the previous itself, it is saying that E1 is twice the input voltage. Input voltage is E. If you can see, E1 divided by E will be equal to 2. That is the answer. So this is the simple question. The answer to this, it is itself given in the question itself. E1 will be equal to twice of E, from where we can get E1 by E will be equal to 2. That is the answer to this question. So now the thing is, for subsequent questions we may require the values of this xi and chi. So if you can see, it is saying let the corresponding value of chi naught is 2 and the xi naught is equal to 0.4 are obtained using the respective curves to design this number. If you can see, what is given is E1 by E is to be limited to 2. If you can see here, E1 by E is limited to 2. Now they have already provided here that they got these values from this graph. In a similar fashion, by this graph itself, if you have any value of this E1 by E, let us say 1, 4, 2.5 or anything, you can calculate the chi and xi values. If you can see here, at this point where E1 by E is 2, we have a chi value that is close to 2, and with rounded off they have taken it as 2. And at this point itself, it cuts this xi naught curve at some point. And if you will draw the horizontal line from this, if you can follow the arrow, it is around like 0.4, and if you round off this, and they have rounded off it around like 0.4. In a similar fashion, you can for different values of E1 by E, you can find this chi and xi value itself by following this curve. So now what we have to calculate is the value of CS, snubber capacitance, in picofarads. So we have I had already told you here itself, you have to just remember this equation. Like this equation will give us the value of the capacitance, snubber capacitance. You have to just remember these two equations. If you can see CS, LP is given in the question itself, that is 8 nano Henry, that is this. And IRR we calculated, if you remember 2 slides back, that is around 8.78 amps. And E is given that it is 50 volts, and chi naught was given in the previous slide itself, that it take it around 2. And if you substitute this value and solve this, you will get the value of CS equal to 61.67 picofarad. That is the answer. The value of the snubber capacitance is like 61.67 picofarad. In a similar fashion, like it is telling, now the next question is find the value of RS. Using this equation, like twice xi naught LP by CS, we can find the value of RS. Xi naught value, it is given, like take it to around like 0.4. LP is given, CS we calculated earlier, like here itself it is 61.67. If we substitute these value, we will get RS value around like 9.11 ohm. So if we design this RC snubber for limiting the peak to 2, we get the values of CS around to be 61.67 picofarad and RS around 9.11 ohms. Second, what it is given is like design the snubber by limiting the dV by dt average, that it has already been given. We had to limit that half of that this. And CS is given here. What is given is CS is given 2 nanofarad is chosen for this snubber. So first we have to calculate dV by dt average divided by E by omega naught. So if we calculate first, what we will calculate, we will be calculating the limiting dv by dt 80. What had been given in the question in itself, like we have to limit the dv by dt to the half of what is given in the data sheet. So in data sheet it is given around 7 volt per nanosecond, and the half of that is 0.5 into 7, that is 3.5 volt per nanosecond. Got it? And if we convert that into per second, that will be equal to 3.5 into 10 raised per 9 volt per second. So also we will calculate omega naught. Omega naught we know it will be equal to 1 by root LP into CS. We know the CS is given around 2 nanofarad, LP is given 8 nanohenry, and from that we can get the value of omega naught. It is 0.25 into 10 raised power 9 radian per second. And now if you take the ratio of this these two, now dv by d average is calculated omega naught, and E we know is around 50, and if we calculate the ratio it comes around to be 0.28 amperes. So this is the answer to this. This is how you have to do the calculation if such question is given in the problem set. So 0.28 amperes is the answer. So now what is being given here is we have to let the corresponding values of chi be given. Now it is given that the chi is equal to 0.9 and xi is equal to 0.5. Using the similar like graph that I had already discussed in the previous slide, now we have to design the snubber in this way. We have to find the value of the R. We know that R will be equal to RS into twice xi naught into LP by CS. We have twice xi naught is given 0.15. For this design, limiting the dV by dt, LP is given in the question in itself, CS was given it to be 2 nanohenry. So R came out to be equal to 0.6 ohm. Now you can see the difference between the two designs. Earlier, like we had the CS equal to 667.67 nanofarad, and R was coming to be around something 8 point or something like that, 9.11 ohm. Here now R is coming, CS is around 2 nanohenry and R is around 0.6 ohm. Third is now we have to do the compromise device for limiting both peak voltage and the dV by dt. So here the first question is we have to calculate dV by dt average and LP. We have to calculate this whole term. So if you can know, we have the limiting value of this dV by dt we had already calculated is 3.5 into 10 raised power 9. Volts per second, and LP is given, it is 8 nanohenry. IRR we had already calculated, it was around 8.78 amps, and E we know that is given is 50 volts. And if you solve this, it comes out to be around 0.0983. We can round off that around to be 0.10. That is answer to this eighth question. Now we have to design like R and C for this in a similar fashion, using the graph like chi naught and xi naught are given around to be 0.1 and 0.9. We have to obtain the values of R and C. So first is find the value of CS. We have to find the value of the CS. We know the CS will be equal to LP divided by IRR square, and this equation. LP we know is 8 nanohenry, IRR is 8.78, E is this, and chi naught is given for this design. For this compromise design, take around to be 0.1, and we can get this CS around to be 24.67 nanofarad. So now you are seeing, if we are having the different designs for the particular application, like for a particular design, if we want to limit the peak, we are having a different value of the capacitor. If we want to limit the dV by dt, then we have a particular value of this capacitor. Now if we want to do the compromise device, then we have a particular value of this capacitor. Now in a similar fashion, now we have to find the value of the RS using the similar equation. Xi naught is given, LPC we calculated right now. R comes out to be around like 1.03 ohm. Here you can see for three different designs, we are getting the three different parameters of values of C and S for a particular design. Uh, Now coming to the question number 11, now it is given from the data sheet, the typical turn off time of a MOSFET is. Now if you like see the switching waveform of this MOSFET, like when this VDS is when VDS goes from blocking to this 0, this is turn on, and this is the turn off. When the VDS goes from like 0 to this rated VDS. So we had seen in the earlier during the switching interval, like how this MOSFET switch, we have this delay time TD off during this our VGS voltage, like during this is the gate during the this charging time of these capacitors TD off, and after that there is that this fall time TF that is given in the current, that is this in the voltage, and our total T off will be equal to TD off and this TF. And the value of this, if you go through the MOSFET data sheet, and the values of these two are given to be around like 39 and 35 nanosecond. So overall T off will be equal to 39 plus 35, that will be around 74 nanosecond. That is the answer to this question. So question number 12, bootstrapping method has the disadvantage of. I think everybody should be able to answer this question, because we had discussed this bootstrapping right now in detail. So can anybody answer? Like there can be multiple answers to this question as well. Can anybody answer? What are the disadvantages of the bootstrapping? Nobody? So yeah, one of the students have answered, and the answer is correct. Is like we have to see the bootstrapping. If you can see the bootstrapping go through, there was no isolation between the power and this circuit side. Then you can see here, because of that thing, there what we saw is there is a low noise immunity between the two sides. So the first one is correct. So second is cannot drive the high side switch. This is wrong, because like bootstrap itself is used in order to drive the high side switch itself. So the B is not the correct answer. Here we are talking about the disadvantages, not about the advantages of the bootstrap. Third part is like applicable only where gate drive require low power. This is also true, because this is a disadvantage. If we want to drive a particular device that requires very high gate current and so on and so forth, and we had seen that this bootstrap capacitor is won't be able to supply that amount of the charge to the device. So this is the correct answer to this, applicable only where gate drive requires the low power. And last is can drive MOSFET but not drive IGBTs. There is no such distinction. It can drive both the devices, and we knew like it can drive the devices, like we need to have an H bridge. We need not to have both devices as the switches. We can have one of the devices the diode and another as a device, and it will be perfectly fine to drive like MOSFET as well as the IGBT. So the answer to the question is low noise immunity, and C is applicable only where the gate drive requires low power. Question number third. The main rule of the snubber power electronics is to convert. We are discussing this right now. Can anybody answer this question? Can anybody answer? Nobody? Yeah, we were discussing this snubbers right now. I think you should be able to answer this question. Can anybody? Nobody is able to answer this. So at least some of you are able to answer. Is feels like you are not listening at all. So we are seeing that the main idea is like during the turn on and turn off, due to the parasitics, like RLC circuit was getting formed, and because of that we had this ringing overshoots and so on and so forth, and spikes we had in the voltage waveform. So the main role of this number was A, to reduce the spike. That is the answer to this question. Reduce the conduction loss. That is not the case. Reduce the inductor size. That is not the case. Change the voltage gain of the converter. That is not the case. So the answer to this question is A, reduce the voltage spikes and during the turn on and turn off times. And with this, this was about the problems that I had to discuss today. And with this, we complete today's problem solving session. If any of you have any questions, you are free to ask. You can text or just unmute or ask. And if not, anyone is having question, then we can close it for the today. Anybody having questions? So if there are not any questions, then we can close today's session. Thank you everyone. Thank you everyone. Thanks.